Sandia National Laboratory's Coyote Canyon Test Complex is located on 40 square miles of plains and mountains just a few minutes from Albuquerque, New Mexico. Coyote is one of the nation's unique testing laboratories, having over 40 facilities where complex problems encountered in engineering analysis can be simulated under closely controlled conditions. These simulations provide response measurements to verify mathematical modeling of these problems. This film shows some of the tests that have been conducted recently at Coyote. This low-level airdrop of a B-61 is a type of weapon delivery that will be simulated at Coyote in the next scene. Here it is dropped from a 100-foot altitude at a velocity of 1,000 feet per second. At Coyote, weapons are accelerated to test velocity on the 5,000-foot rocket sled track. There they are ejected to test altitudes of up to 250 feet. Once at altitude, the trajectory is similar to the airdrop. The luminescent spot on the side of the weapon is a reflection of a laser beam. The beam, transmitted from a tracker and returned to the tracker by a reflective material, provides the means for automatic trajectory measurements. Computers in the laser tracker provide real-time trajectory data of sled acceleration and weapon ejection for directing other equipment, such as this slave tracker used for photographing tests from a different position. Hard copy data are available immediately after the test, eliminating data reduction delays. Sled testing offers the most convenient means for testing air-deliverable weapons at preconditioned temperatures. Temperature shrouds are removed from test vehicles just prior to launch. Another advantage of simulated weapon delivery at Coyote is precision. A precision possible because sled velocity, weapon release point, and ejection altitude can be closely controlled. Thus, a weapon can be placed exactly where planned, for example, onto this special target. Collecting data during a test is often a greater challenge than conducting the test. Reliable response measurements are essential in developing improved mathematical models. To fully instrument test devices during impact, Sandia pioneered the reverse ballistic technique, accelerating the target into the test device. This in slow motion is a soft target impacting the Boeing version of the W-80 air-launched cruise missile at 815 feet per second. The reverse ballistic technique allows a wide variety of high-frequency data to be transmitted via hard wire to recorders in a bunker adjacent to the sled track. Reverse ballistics again, in real time, a 12,000-pound target impacts a Lance missile at 2,700 feet per second. At speeds beyond about 4,000 feet per second, the reverse ballistic technique is impractical. So another innovative way to collect a limited amount of data was used during tests of the Mark 12A fuse at 6,000 feet per second, the sled's maximum velocity. These fins on the sled cut this screen attached along the rail. During impact, data traveled from the fins through the screens to data recorders. In addition, the moment of impact was captured by rotating mirror framing cameras developed at Sandia for the photometrics group. The cameras reach speeds greater than 250,000 frames per second. It may someday be necessary to launch missiles through clouds of dust. To determine the extent of dust erosion on proposed missile skin materials, predetermined sizes and amounts of sand were shaken down across the track as a sled carried candidate materials at 3,000 feet per second. Not all sled tests involve weapons. The Department of Energy sponsored tests of nuclear spent fuel shipping casks, rugged enough to survive these severe transportation accidents without releasing nuclear materials, all at 80 miles per hour. The railroad car and cask were then taken to Coyote's burn site. 36,000 gallons of burning jet fuel subjected the cask to a temperature of 1,900 degrees Fahrenheit for 2 hours. This test for the Electric Power Research Institute, or EPRI, simulated the response of a parked car to a 300-mile-per-hour tornado. As predicted, The car, once released from the sled, rose and fell a few inches, but was held in place by tire friction and did not become an airborne hazard. Once the sled was braked, of course, the car's momentum propelled it into the safety barrier. EPRI sponsored tests to assess the threat of turbine missiles to reactor containment buildings in nuclear power plants. A segment of a steam turbine rotor was impacted into its ring and casing structure at 480 feet per second to verify predicted escape velocities. Turbine missiles were then impacted into simulated containment building walls at the established escape velocity. Wall response recorded during impact is being used to assess containment building vulnerability. This thunder tube simulates overpressures from explosions. The 19-foot diameter tube can test a device up to 15 feet long. The umbilical attached to the device permits up to 200 channels of hardwire instrumentation to be received during engulfment. Up to 350 pounds of high explosive is detonated at the driver end, generating maximum overpressures of 100 pounds per square inch at the test station. Explosively driven flyer plates are used to obtain the response of nose cones impacting targets at speeds beyond rocket sled capability. Data are recorded on X-ray and high-speed cameras. This footage of a rotating flyer plate striking a nose cone at a predetermined angle comes from a rotating mirror framing camera. Impulse testing is done with light-sensitive explosives, sprayed on remotely. The facility can simulate impulse levels as high as 5,000 taps. After spraying, the device is moved in front of a light bank that initiates the explosive. This is a SRAM missile dropped from an F-111. The missile experiences 5 Gs as it maneuvers away from the aircraft. At the centrifuge complex in Coyote, a similar missile at the end of a 35-foot boom receives 11 Gs prior to rocket ignition. Here is an overhead view of vibration and acceleration combined, created by mounting a vibration machine at the end of the 26-foot centrifuge. Both of these centrifuges are among the world's largest and are driven by the same power supply. Each of them can produce 240 Gs. The aerial cable is suspended between 2 peaks 5,000 feet apart. A rocket sled can pull a test device from the cable down to a target at velocities up to 1,000 feet per second. These two tests contrast the effect of a weapon containing traditional high explosive detonating as it hits a hard target at 800 feet per second, with that of the same weapon at the same velocity with non-sensitive high explosive that does not detonate on impact. Drop tests from the cable demonstrate the SATARM anti-tank weapon. As it drops, it rotates, searching for a target. Once it locates an object that matches the definition of a tank programmed into its memory, it fires a self-forging projectile that can penetrate the tank's armor. The projectile left this hole as it entered and destroyed the interior. Aerial trolleys on the cable can simulate aircraft flight. In this test, a thermite burner provides a heat source equivalent to that of an aircraft tailpipe. When a heat-seeking missile is fired, a detector in the trolley senses the oncoming missile and fires a flare. The flare decoys the missile, and the missile intercepts the flare a safe distance from the simulated plane. Currently, the largest solar test site in the world is this central receiver test facility at Coyote. It is used to evaluate the performance of a variety of solar components. The sun tracking mirrors concentrate solar energy at the top of the tower to produce heat that could be used to generate electricity. Complementing the work at the Central Receiver Test Facility is a program designed to provide an understanding of problems caused by unsteady boiling phenomena in a solar receiver. A portion of a steam boiler was placed inside Coyote's unique radiant heat facility. It uses infrared lamps to heat even large devices as high as 2,000 degrees Fahrenheit. As these film clips have shown, the Coyote Canyon Test Complex is a unique collection of simulation facilities. It continues to play an important role as an accessible and economical place for testing advanced weapon designs and concepts, as well as a site for testing energy-related devices. Coyote is a national resource available to all R&D agencies who wish to utilize its unique capabilities.